Section 2. Timing and Scheduling in Unity 3D. Fixed update versus update. Timescale and time.time. And physics. Everything in Unity is metered out on the fixed update. Update happens in between fixed updates. To do this, the algorithm is as follows. 1. Calculate the physics as they would be one fixed update time step from now. 2. Render the scene at this time. This is the minimum amount of effort that would be required. 3. Repeat this for any additional frames that can be rendered before the deadline, interpolating the physics data. In the diagram shown, first, frame 1 is drawn because this is the minimum amount of effort required before the deadline. When the deadline occurs, frame 1 is swapped in. In the second figure, we see how the algorithm would behave if there was additional time. In particular, frame 0 is drawn because there is time before the deadline where frame 1 must be drawn. As you can see, this means the fixed delta time should be reasonably constant, which is important for the physics model, but the update delta time can vary wildly. Fixed update events fire at a fixed interval, and the update event fires every time there is time available between them. If any time is left after an update event and before the deadline, another update event is fired. Sometimes a calculation, an update, or physics update may take too long. Or Unity may misestimate how much time is needed to calculate an update before the deadline. When this happens, we incur frame debt because we're late on the deadline. To mitigate the debt, we use a mechanism called frame dropping. In frame dropping, we forget about rendering the next frame because we estimate that it will be too late if we try anyway. Instead, we render a frame ahead or several frames ahead. Therefore, since our frame updates are less frequent, our frame is dropped. The frame rate is just the number of updates that can occur in an arbitrary interval. There are many kinds of frame rate, including the speed of the simulation, the speed of the render, and the speed is limited by behaviors. Why might we choose to change the fixed time step? The most obvious answer is the discrete physics model. Unity's default physics model is to calculate where an object will be in the next fixed time step, and then resolve any intersections into collisions. If an object is moving at high speed, this can fail because the next position may be clear of the object it should have hit, as shown in Figure 1. To fix this, we could make the fixed time step shorter, but this would usually be an inefficient use of resources, unless the problem is extremely common. Instead, we apply a continuous collision detection model to the object experiencing the issue. This causes the collision algorithm to test against a volume swept along the rigid body's vector of motion. For example, with a sphere, a capsule test would be used. A capsule is a sphere at the start and end points with a cylinder in the middle. Another time setting is the timescale. The timescale effectively changes the speed of the simulation. A timescale of 1 is unscaled. Above 1 is faster, below is slower. For example, a timescale of 0.5 would be half the speed. Of course, Unity is still limited by how fast it can render, so faster timescales will result in more frames dropped, and slower speeds will result in fewer. Timescale can be used for fast and slow motion effects. In addition to fast and slow motion effects, there is a practical upshot to changing the timescale. We can smooth out spikes in frame dropping by marginally slowing down every frame, effectively pushing back the fixed deadline. The most common use of the timescale is setting it to 0 to pause the game while in a menu. Time settings are accessible in the project settings under the time section. These settings are the defaults the game will use while running, but they may be set programmatically with the time class. One such setting which we have yet to mention is the maximum allowed time step. This value is the hard limit on how much time the physics calculation can take in fixed update, preventing the CPU from monopolizing time that would be needed for rendering. There are a few rules that should always be observed when using the default update loops. Recall that timing is essential for physics simulation, so all physics-related changes to the scene and calculation should occur in fixed update. Similarly, player's input, keyboard, mouse, touch, or otherwise is read in update, so the player's input should always be interpreted in update. Because these loops must remain separate, you should store values they have to share in a shared object, such as the member variables of a script. We'll take a look at this again in Section 6. Since anything aesthetic has nothing to do with the fairness of the game, it can usually be scheduled at an arbitrary time, including outside of these main loops. I've prepared an experiment to observe the frame rate of the game at runtime. You can obtain it from the exercise files from this section. I've created a script called FrameRateMonitor. As the name suggests, it keeps track of the runtime frame rate of the game. To check the frame rate, we check whether an arbitrary interval has elapsed within update. To do this, we store the last check time and see what the difference between the last check time and the current time is. If this interval has elapsed, we check how many frames occurred within that interval using the same logic. Finally, we update the start of the interval with the current time and current number of frames. Then we average the number of frames that occurred over the interval. We have two averages, the localized frame rate and the marching frame rate. The localized frame rate is the amount of frames that occurred in the last interval. The marching frame rate is the average of the last interval and the current interval. The marching frame rate is less susceptible to spikes in frame rate, so you can use it as a more stable estimator of the actual frame rate. Additionally, I've introduced two events which you can use to determine how you would like the game to behave at runtime: on low frame rate and on high frame rate. You can use the on low frame rate event to determine how your game behaves when the frame rate is unacceptably slow, turning off some rendering or effect features. Similarly, when the frame rate is restored to an acceptable level, you can turn these features back on and even turn on some additional features. Go into Unity and attach this script to an object. Then run the game and observe the results in the debug log. I've saved an example scene which contains this setup in the example scenes folder in a scene called FrameRateMonitor. You may have been surprised to see in the results that the frame rate was lower than the frame rate you may have actually been expecting, especially if you have seen the frame rate in the Unity stats window. This is because the Unity stats window shows the graphical frame rate, the rate at which the hardware could theoretically render the scene. The GPU renders far more frames than actual update frames occur. This prevents jitter because it means the GPU can always render a fairly accurate picture of the scene, even when the frame rate is highly variable, as in the update frame rate. We need to move on, so we won't go further into it, but this comes up a lot in audiovisual workflows and is called supersampling. If you have the time, it's worth a read. When the CPU or GPU is preventing the scene from rendering at a reasonable rate, this is called a bottleneck. A bottleneck is when the slowest part of a process slows down the entire process, despite other parts of the process being fast to complete. We will return to bottlenecks in Chapter 3.1.